And with that, Torsten, would you like to get us started?
Yes, thank you very much. It's wonderful to have Song Han here to give us the master of tiny deep learning. And let's get started. And Nikolai is introducing him.
Okay, thank you, Torsten, and thank you, Song, for agreeing to give a talk. So Song Han is an assistant professor at MIT's Department of Electrical Engineering and Computer Science. He received his bachelor's degree from Tsinghua University and his PhD from Stanford. His research, as Torsten said, focuses on efficient deep learning, both models and hardware. He's won a number of awards and competitions for efficient deep learning and has received a lot of recognition both from industry and also an NSF Career Award. And without any further ado, take us away, Song. Thank you.
Hey, thank you. Thanks for inviting me here. So today I'm glad to present our research on TinyML and efficient deep learning and how to put AI on a diet. So we know today memory is too small to hold DNNs on these mobile devices and also these IoT devices. So we believe the future belongs to this tiny AI where we no longer have to send the data to the cloud, and it's very cheap. And it's very low power and with small form factor can be everywhere in our lives, in smart factory, smart building, smart home, and also in ADAS. But it's very challenging because these tiny AI devices like microcontrollers, their memory resource is orders of magnitude than these mobile devices and cloud devices. Like a GPU has 16 gigabytes of memory, and nowadays it is even larger, like 48 gigabytes. A mobile phone can easily get 4 gigabytes of memory, but these tiny microcontrollers has only hundreds of kilobytes, like this STM32M7 microcontroller has about 320 kilobytes of memory. And the storage, the flash, which is read-only, is only 1 megabyte. And we found such tiny model design is fundamentally different from these existing models like MobileNet. It has no DRAM, no operating system, no virtual memory. And we cannot directly scale these previous models like MobileNet or ResNet, since due to the non-proportional activations and parameters. So let's first review some of the prior work I've done before. So the algorithm is called deep compression, where we can reduce the model size and also the activation size of neural nets to make it run fast and efficiently with limited hardware resource. By pruning the model and enable weight sharing, deep compression can reduce the model size of ResNet 50 from 100 megabytes to only 6 megabytes without losing accuracy. And recently, pruning and sparsity has gained increased attention since 2015. If you see the publications per year, is less than 250 before 2015, and it's suddenly surged because both the deep learning community and also the hardware community are beginning to seeking methods to utilize pruned model and sparsity in AI accelerators. For example, nowadays, the sparsity is natively supported in NVIDIA A100 GPUs with 2 to 4 sparsity. So every 4 elements, 2 of them must be 0. So theoretical speedup is about 2x, and the measured speedup is 1.5x. Also, Xilinx, the Xilinx Vitis AI also support pruning and model compression. And after that, we ask ourselves the question, can we design even smaller models that is automated without using a lot of human tuning? Okay, so conventionally, either model compression or quantization, that require a lot of human intervention, a lot of tuning. For example, in the first couple of layers, we want to prune less number of weights since they interact with the image directly and has and extracts low-level features, has less redundancy, and those later layers tend to have more redundancy. Okay, Therefore, we have a lot of handcrafted heuristics to guide the pruning process. How much do we prune for each layer? And later we designed an automated tool called AutoML for model compression, where we have a push the button solution. Basically use a DDPG agent, a reinforcement learning algorithm, to find the layer by layer sparsity. What is the optimal sparsity for each layer with the reward of latency, with latency flops, and also the accuracy. Okay, and we find this method works really well by giving the action for each layer, which is the sparsity, and collect the reward, and try to encourage low flops and high accuracy. We can prune resident 50 by 5x without losing accuracy in about just a few GPU hours. Compared with during my PhD thesis, I compressed resident 50. It took me a week to do all the trials and errors and just prune it by 3.4x. And next, rather than pruning an existing model, we started by neural architecture search, try to find an efficient architecture that is small and compact to begin with. So this process NAS paper came under the motivation that conventional neural architecture search is very expensive. So people have to rely on those proxy tasks. For example, search the architecture on Cypher and then transfer that architecture to ImageNet. Or people can just train a few epochs and then use the accuracy, the partially trained accuracy as a proxy as the full accuracy, which suffers from some models may be fast to train in the beginning but slow in the end. And also people use proxy tasks, for example, repeat the building block just to learn one building block and stack the building blocks together. Okay. But proxy-based NAS try to conquer this by making the architecture search efficient, both memory-wise and also latency-wise. So we introduced these architectural parameters. That is the probability of choosing each path. So each path could be a count of 3x3 convolution, 5x5 convolution, and density mapping or pooling. And we like the algorithm to learn itself what is the probability for choosing each path. So at training time, we sampled the path according to the probability. At test time, we just pick the path with the highest probability. So in this way, we can also make latency differentiable, or we can also use the reinforced algorithm to learn both the weight parameter and architecture parameter in the single pass. And as a result, the search cost is only 200 GPU hours compared with 48,000 GPU hours in prior neural architecture search work. And compared with darts, we have only one path residing in memory. So this is also memory efficient. So in this way, we can enable neural architecture search to take the same cost of just normally training a model. So we can remove those proxy tasks and achieve very good results. For example, getting the first place in the Visual Wake Words Challenge in 2019 with a peak memory usage smaller than 250 kilobytes, model size smaller than 250 kilobytes, and the number of max is smaller than 60 milli. And finally, we also automated the process of quantizing the model. So many modern AI chips support mixed precision inference. So we can have 4-bit, 2-bit, 6-bit, etc. for weights and activations. But how to optimally select the optimal bit with the precision remains a challenging task. So we applied a similar algorithm as this AMC, the AutoML for model compression, to make it hardware-aware automated quantization to select the precision for each layer, and then collect the reward, and finally encourage high accuracy and low latency and low energy. However, we find those solutions still there is a big gap between what we have and what we want. We find existing work. The existing work only reduces on the model size, like from ResNet to MobileNet, the number of parameters reduced by 4.6 times. Okay, that's very good. However, the bottleneck, which is the activation, is actually 1.8 times bigger. It didn't get decreased, but even bigger. This is due to the inverted bottleneck, which is highly inefficient, expansion ratio of 3 or 6, which occupied a lot of intermediate activation. And our budget is only 512 kilobytes, but MobileNet gets even bigger. So we propose this MCUNet, which is targeting specifically for microcontrollers by optimizing the activation memory to let the neural network consume less intermediate activation, the peak memory, so that we can reduce the peak memory by 3.4x compared with the MobileNet family. So that rather than previously, we can only do those toy examples like classifying apples and oranges. Now we can do 1,000-class ImageNet classification on these commercial tiny microcontrollers. So compared with TF Lite Micro plus MobileNet V2, which is scaled to fit a Cortex M7, ARM Cortex M7 microcontroller, which has only 53.8% top-line accuracy, we can improve the accuracy to more than 70.7%. So this is a big improvement of the accuracy, saying that actually we can do a lot of complicated vision tasks on these highly resource-constrained microcontrollers, these IoT devices. Okay, so here we have some comparison of these different frameworks. So part of the MCUNet, we also co-designed the TinyEngine, which is an inference engine. So compared with these modern inference engines, such as TensorFlow Lite Micro, MicroTVM, the tuned version of that, and the CMC's TinyEngine ranges from 2.7 to 4.8 times smaller compared with these devices. And also we compared the speed up. So TinyEngine ranges from 1.5 to 3x faster than these existing frameworks for microcontrollers. And here we have a breakdown combining Tiny Neural Architecture Search, TinyNAS, and Tiny Inference Engine, the TinyEngine. So the task is ImageNet classification on STM32F746 MCU, which has 320 kilobytes and only 1 megabyte of flash. So the baseline is by using the MobileNet V2, scale down to fit the microcontroller, okay? And by using ARM CMC's, we can get only 39% top-line accuracy under such memory constraint. And by system level only optimizations, we push the accuracy to 49%. And by model optimizations with TinyNAS, we push the accuracy to 56%. And by co-designing the TinyNAS and TinyEngine, we improve the accuracy to 62. Okay, so let's see what is inside the TinyNAS. So we want to break the convention of this labor-consuming human design of neural nets to make it automated and automatically fit different devices, both a large device like Cortex M7 and a small device like Cortex M4. They have different resources like Cortex M7, this is STM32H743, that has 512 kilobytes of SRAM and 2 megabytes of flash, while a Cortex M4 has only 256 kilobytes of SRAM and 1 megabyte of flash. Okay, and there's even more diverse configurations for different product lines. So if we train different models targeting different constraints, it's very difficult to train models of different sizes to fit different devices. Therefore, we propose this once-for-all network. The idea is to fit diverse hardware constraints by training once and get many subnetworks. For example, we can select a larger subnetwork targeting a Cortex M7, a stronger MCU, and we can select a smaller subnetwork targeting a weaker MCU like Cortex M4 MCU. And also, we also want to be inclusive for users, different users. Some users may have high-end phones, okay, and some of them may have low-end devices. And we want to be inclusive for users who have these low-end phones as well, but it's super expensive to design neural nets of different sizes. But with once-for-all model, we can pick a larger subnet for a newer, like Samsung Note 10, and a smaller subnet for a even older, like Samsung S7. And we can either also fit diverse battery constraints, okay, by picking different sizes of subnetworks, like a full battery case, less battery case, and even the battery saving mode. So by using this once-for-all network, we can design specialized model by training only once and get different subnets for this small MCU and the large MCU. And this is the accuracy for different cases. We can see a larger, stronger MCU definitely give higher accuracy. And this is the first to achieve more than 70% ImageNet top-line accuracy on commercial MCUs. And this is about 17% accuracy improvement compared with the Google solution MobileNavi2 plus ARM CMC. So this once-for-all network is scalable not only on microcontrollers, but also on these mobile phones, like Samsung phone, Google phone, LG phone, compared with the baseline, which is MobileNavi3, as well as the MobileNavi2 on this NVIDIA GPU, Intel CPU, and Xilinx FPGA. We can see on NVIDIA GPU, the latency is improved from 28 milliseconds to only about 12 milliseconds, while giving better accuracy, or the 2x speed up. And on Xilinx FPGA, the latency reduced from 6.5 milliseconds to about 4 milliseconds by using this Vitus AI toolkit. So here we can compare with the EfficientNet. So the similar with 80% accuracy, maybe even better. Wi-Fi is 2.6 times faster or 3.8 higher accuracy compared while using the same latency. And we can train once and get the entire Pareto optimal curve. Okay, get the entire Pareto optimal curve. Compared with conventional models, we train 4 times. Well, we can get 4 models, but we have to train 4 times. Now we train only 1 model, but we can get many different models in this whole Pareto optimal curve, saving the training cost and carbon emission. So here we see the trade-off of accuracy in the y-axis and max in the x-axis for different neural nets from Resident 50, Resident 101, exception model, inception, proximate NAS, and here is once-for-all. So here it has very low max, but pretty good accuracy. Okay, 595 million max and 80% top-line accuracy. And recently, Alibaba find this improvement, this accuracy can be even improved by using even larger data set. So it has very strong scalability, and this achieved the world record in the MLPerf benchmark by Alibaba using this once-for-all network, achieving more than 1 million images per second, running on 8100 GPUs. So this once-for-all model achieved several awards in the 3rd, 4th, and 5th low power computer vision challenge, multiple hardware platforms, CPU, FPGA, DSP, classification and detection, and also visual wakeford challenge, semantic kitty segmentation, which I will talk about later for this point cloud, and also the NLP track in the MicroNet challenge. And later, we want to further open the design space, considering not only the neural network architecture, but also the mapping and also accelerator architecture. So we propose this NAS, NAAS, there are 2 A's, so neural accelerator architecture search. Okay, so we co-search the best neural net using evolution, and also the accelerators, hardware accelerators architecture, including the topology, the array size, the width, the buffer size, etc., and together with the mapping search space. And all these are using the evolution strategy to find the optimal solution. And with this approach, we can reduce the energy delay product by 4.4x with only the hardware and compiler mapping search, and further improve the accuracy by 2.7% by this co-search. Hey, let's now see some applications. Focus on this large-scale data sets like ImageNet, and also these wake words tasks like visual wake words, detecting person or no person, and also these speech commands tasks. So on visual wake words data set, we can improve the latency by like up to 2.4 times faster, and the SRAM usage is reduced by 3.7. And here is our budget, which is 256 kilobyte of constraint on these microcontrollers. And our MCUNet v2 even push this even further by 4 to 7 times reduction for the latency and SRAM usage. And this is the result on the audio wake words, which is the speech command. Okay, and this is 2% higher accuracy or 2.8 times faster inference latency. And again, everything is measured on this MCU. Here we have some demos for the visual wake words running on this STM32F746. Accuracy improvement is 12%, and the frame rate improved from 2.9 FPS to 7.3 FPS. And not only classification, we are very early to do such detection on microcontrollers. So this is face and mask detection on the same microcontroller. Green for mask and red for no mask. And also person detection on this same STM32 microcontroller. Okay, so we think autonomous driving is another key application for this machine learning on the edge. For example, AR and VR. People used to have a whole backpack of computers just because the computation is just so expensive. The resolution is high, the latency has to be low. And for self-driving, a whole trunk of GPUs, because multiple sensors, very heavy computation. And mobile phones are now equipped with LiDAR sensors, but they have limited amount of memory. Our solution, SPV-NAS, stands for sparse point voxel neural architecture search, can significantly improve the latency with very good accuracy, ranking top on the leaderboard. And in particular, the idea of point voxel convolution lies in that point cloud is highly sparse, and sparsity is not hardware friendly. One idea is to quantize them into voxels, voxelize those points into different grids. But the resolution of the grid, the memory of the total memory consumption grows cubically with the resolution. Okay, so we cannot have a very high resolution voxels. Therefore, we compensate the voxel branch with a multi-layer perception, which is a point branch, okay, which captures those fine-grained features. Well, this voxel branch captures those coarse-grained neighboring information. Okay, by combining these two branches together, we can drastically improve the accuracy on these small objects like person, 5% improvement, bicycle 11%, motorcycle is 25%. And we highlighted these small objects that is correctly paid attention by this multi-layer perception, showing the importance of this point branch combined with this voxel branch. So in this way, we can accelerate these models by up to 2x on these Jetson devices, Jetson Nano, Jetson TX2, Jetson NX Xavier, Jetson AGX Xavier, which was highlighted as the project of the month by NVIDIA Jetson community. Also ranks top on the semantic leaderboard, and with quite a significant speed up for both indoor scene and outdoor scene scenarios. And recently, we participated in this auto driving challenge for semantic segmentation. And again, this SPVCN ranks top of the leaderboard with better result than Google, Huawei, etc. So we deployed this efficient LiDAR perception on a full autonomous, on a full-scale vehicle in real world. So the LiDAR sensor generates 3 million points per second, which is sparse and has a lot of memory consumption. This fast LiDAR net, we accelerate the inference from 5 frames per second to 47 frames per second so that it's able to drive a car in real time. This was published in ICRA 21. We even built a hardware accelerator to co-design the neural network architecture with the silicon implementation. And this achieves about 4x speed up compared with the GPU and over 70%, 70x improvement over CPU and TPU due to we reduce a lot of memory movement and use a sorter array-based method to find the neighbors. And another key application is GANs. GANs is super computationally heavy because it has to do pixel-wise prediction. And we accelerate that by reducing the computation from 56 gigaops to only 3.5 gigaops. Okay, so 16 times reduction about the computation flops. So we can very quickly quick inference for these GANs. This is another demo for interactive photo editing. So for example, making the lady smile takes about 3.04 seconds on a MacBook. This is not interactive, it has a long latency. We can also make her look younger, but we also want to have low latency inference. Therefore, we applied this once for all network and try to make this once for all GAN. We call it any cost GAN. So even with low cost inference, we can still guarantee high quality. For example, we can switch to any cost GAN and redo the task on the same laptop. Make her smile. Now it's becoming much faster. Only 0.39 seconds on the laptop. And when we finish, we can click the finalize button to call the full network. Takes 3 seconds to predict the final rendered image. We can see another example. Using any cost again, we can make him look younger. When making him look older, usually that's associated with eyeglasses. So we can also remove the eyeglasses by switching the bar to the left. Add some mustache. And then finalize. We see finalize takes a longer time because it's running the full model, but such interactiveness making it be able to be low latency on this laptop or those mobile devices. That's very crucial for interactive editing. Okay, and let's also see some effect of this any cost again. With 100% of computation, these are the generated faces. They look very photorealistic. And we can reduce the computation all the way to, let me see if this is a video. Yep, we can reduce the computation to 78%, 59%, 39%, or even 19%. Okay, we can see the generated image's quality is pretty, still with high fidelity. Okay. Okay, so another application of this once for all model, we also applied once for all to NLP models. So the work is called HAT, hardware aware transformer. We can select a larger subnetwork for powerful tasks, powerful hardware platforms, and select a smaller subnetwork for edge devices like this Raspberry Pi CPU. So with hardware-aware transformer, we can make the model 2.9 times faster compared with the baseline transformer big, while having similar BLEU score. And we can further compress the transformer to up to 25x by applying HAT and other general model compression techniques. Another idea is cascaded token head pruning for this NLP task. We know the human language is highly redundant, so we've applied this cascaded token head pruning to gradually prune away those redundant tokens. For example, in this sentence, it has 11 tokens as a visual trait. The film is almost perfect. We can prune it to only 5 tokens and treat the film perfect. And in the third layer, we find we need to keep only 2 tokens, film perfect. Therefore, only 12% of the tokens are left. So in this method, we can achieve a 3.4x speedup with such cascaded token head pruning, and another 22x with a specialized ASIC data path, and another 2.8 times speedup with progressive quantization. Okay, so we also applied TinyML techniques to video recognition. So this is reducing the latency by 9 times with this temporal shift module. And this is the throughput improvement. Each row is a row of videos. Previously, using the i3D method, it can run 6.1 videos per second. You see the bar is moving very slow, but with temporal shift module, TSM, video recognition becomes 12.7 times higher throughput. Therefore, we can see the bar is moving much faster. So let's now switch gear from inference to training. So we also want to enable training or transfer learning on these edge devices, because users want to customize their data without leaking the information to the cloud. So AI systems need to continuously adapt to new data collected from the sensors. And such data cannot leave the devices because of security and regularization. And our technique called tiny transfer learning can reduce the training memory from, which is the main bottleneck for training due to the batch size, and also due to the forward and backward. We have to keep all the intermediate activations for backward, rather than we can throw away one layer after we inference. We are inferencing the next layer. So tiny transfer learning can reduce the training memory from 300 megabytes to only 16 megabytes. That is achieved by the observation that weight update is very memory expensive and the bias update is quite memory efficient. Okay, so during backward, we no longer update the weight, but only the bias. However, such method will limit the model capacity. Therefore, we added a light residual module, which is replacing the 1-by-1 comp and depth-wise comp, which is inefficient due to the large expansion ratio, with a a single layer, either a normal convolution layer or just a group-wise convolution layer. Okay, and we no longer have a large expansion ratio like 6, but very 1/6. We use 1/6 of the channels and half the resolution and 2/3 of the depth. So in this manner, we can achieve very decent saving for the training memory. So on these 3 different data sets, flowers, cars, and food, the training memory is reduced from 4.5 times to 6.5 times. So on different data sets, TinyTL provide such significant memory saving, but that's not the end. We can even push it further to squeeze it to the size of L3 cache, which normally all the CPU processors now have tens of megabytes of cache. If we can enable training everything in the cache, that is super fast. So we further propose to apply group normalization during the training process. And we can further enable batch 1 training to converge to the same accuracy as a normal training, so that we can have a very low training memory, so only 16 megabytes. Okay, so above are the techniques for both inference and training, targeting mobile and edge devices. We find another aspect of efficient deep learning is the data efficiency. Nowadays, people require a lot of training data to train these models. If we train, for example, train GAN using only 100 images, the quality degrades very quickly. So without our technique, if using only 100 images, this is the quality of the Obama face generated by GANs. But with our technique, the quality is much better. Okay. So this is the quantitative study from 100% training data to 10%. Without our technique, the normal technique, the quality degrades very quickly. So the higher the FID, the worse the quality. But with differentiable augmentation, we can match the state of the art using only 20% of the data. Even 10% of training data, the FID is still reasonable. And now we show some demos of training GANs using only 100 images. The generated faces, animals, and these these architectures from different angles, different seasons, from days to nights, they generalize really well, not just remembering the training data set, but with smooth interpolation. And everything here is open sourced on our GitHub. Feel free to try it out and generate your own images using only 100 training data. All right, so in summary, we are in the age of TinyML, and there is a promising trend that we are able to squeeze lots of the cool applications, not just toy application, on IoT devices. So from cloud AI, where we have ResNet, to mobile AI, where we have MobileNet, to this tiny AI on these microcontrollers, we believe the MCUNet can help a lot for the community to grow. So this is an exciting area, and thanks to my students, and thanks all for your attention. That's all for my presentation.
Thank you, Song, for the excellent talk and also the lovely videos and demos. Before we move to questions, just a note that our next BCAST seminar will be on the 26th of August. Please check our website for details.